All right. I brought that up so I could talk about something else. This is an idea I had just the other day. I haven't coded this up. It's completely untested. I'm just throwing an idea at you. Tell me what you think. Remember in assignment 4, I think it was, we did convolution? Was that 4? Okay. And the idea of convolution is we usually take an image. Here, I'll draw a picture so it's clear that it's an image. There's the sun. All suns must be smiling and have rays streaming from them. Okay. This is an image, and we pass that through some set of filters, which we often draw as a cube, so as to indicate that the square portion is the filter and the depth of that is the number of filters that we're applying to the image. And if we run that through convolution, then we ultimately arrive at something that ends up being itself a multidimensional image, and we repeat. And to distinguish the filters from the outputs, I'll make the filter blue. And close off that little tiny hole through which it escaped so I can fill in the rest of it. Okay. Multiple layers of convolution is a really great way to digest images. One of the problems with convolution is that we've got these images, and every image is represented as a massive 2D array of pixels, and that just doesn't scale well. Usually in most papers you'll see that they scale it way down to like a 256 by 256 pixel image. Why do they do that? Because if you feed in a great full 4 megabyte pixel image as it comes right out of your digital camera, you're going to be doing number crunching for the next 6 years as you try to train this darn thing, right? So pixels just don't scale well. But remember in the thing we were just talking about, if we put the pixels on the output end of the image, we only need to use a 1 pixel camera, and we can actually use a much smaller neural network, and it scales much better. Remember all of that? Okay, so the idea that I was thinking of is, hey, this is a discretized representation of the image, but what if we thought of an image as a continuous function rather than as discretized thing? Could we actually feed a continuous function into a convolutional neural network and get it to work somehow? Turns out the answer is yes, because convolution itself is actually a continuous operation. And when we do the discretized version of convolution, it's just a discretized version of convolution. Point is, convolution can be done with integrals instead of discretization. So how would we possibly represent our filter as a continuous function rather than as a matrix or tensor of weights? Well, here's what I'm thinking. Suppose we use a neural network, because neural network is my solution to everything. If you ever wonder what my solution is, the answer is use a neural network. Suppose we fed to this neural network as inputs, I'll just call it x1 and x2, where x1 and x2 now represent the horizontal and vertical positions on the filter matrix, the row and column of the filter, and the output I'll say is E for element. I shouldn't use E, that sounds too much like error. How about F for the filter element? Do you see that this neural network, the F now is a continuous function of 2 inputs, and so this whole thing is the same as a matrix filter, right? So we have a whole bunch of filters here that we're applying to our image, but now I have a continuous filter represented by this neural network. Could I not then replace this whole filter with this whole neural network? Okay. And then if I have a continuous input image, now where am I going to get a continuous input image? They always come in discretized form because that's what our digital cameras give us, right? But if I wanted to, I could use interpolation to approximate what it would look like if it were a continuous image. So let's suppose I just simply use interpolation, and so now this thing is like a continuous image. And now I have a continuous function here, and if I do convolve this continuous image with a continuous filter, I'll get a continuous output, right? Then I could make 20 layers of that, and I have a totally continuous convolutional neural network. Is that a thing? I don't know. There's probably already a paper out there, but this is what I was thinking about on Sunday when I was supposed to be paying attention in church. And so now, let's see. Imagine that we've got many layers of this, and we finally compute this output, and we're mapping from a continuous image to another continuous image. Let's suppose this is the predicted, and this is the target. Well, we could certainly pick a single pixel at random from this target image and compare it with the corresponding generated pixel, right? And we could take the difference between those and backpropagate it as error. But couldn't we then backpropagate it right down into this function and change the weights inside of here, which would effectively update this filter? And then couldn't we keep backpropagating it through here and propagate it right down into here and update the weights inside of there, which would update this filter? Do you see how we could basically train a neural network that's totally continuous? Well, then here's what I was thinking. Instead of visiting all of the pixels in this image, what if we think of it as continuous? So there's an infinite number of pixels there, but we just visit one pixel at a time using my MCMC approach that we have here. Not MCMC, Metropolis Hastings approach. So we're going to sample the image based on where we're already making bad predictions. And as we sample that image, we're only taking a single value here, so it'll be rather rapid, and then we'll backpropagate it back into here. And it seems to me that we're now doing kind of an online or stochastic training process that used to require taking all the pixels in an image and doing a whole bunch of math to feed them through at every layer. If I'm doing one pixel at a time now, it's going to be blazing fast compared to what it was before. And if it's focusing on the regions of the image where it's doing the worst, I think it should learn to fit the image much more rapidly, and I'm hoping this will turn into continuous convolution. Yeah.
So are you having this one neural net for the filter, right? Even though you're having multiple, you're creating a tensor out of it, right? So you have multiple filters with all that one neural net?
Yeah. I mean, if I wanted to have a 3 tensor instead of x1 and x2, I'd feed in x3. There, now it's a 3-dimensional continuous function.
Okay, yeah.
So yeah, this is, a neural network can very well represent a continuous tensor of any arbitrary dimensionality, where the inputs just specify the location on the tensor, so to speak. The more I've been thinking about this, the more I've come to the conclusion that you always, at every point, you actually, in order to sample using Metropolis, you actually have to do 2 points, the current one and the candidate one. And in order to do that, I'll need 2 points from the input image so that it can be sampled as well. And so for every layer I go back, I have exponentially more sample points I have to use to do my MCMC. So that might kill the performance. I don't know, but I'm still toying with the idea. And I wanted to throw this at you just so that I have thrown some random research ideas at you and see what you think. Does this spawn any great ideas in anybody? Of course, it shouldn't yet. I mean, you've just only heard about it. But I think there's a certain amount of value in being able to consider and evaluate something that's utterly never been published before. No one's even run an experiment on it. And yet I think you guys probably know enough to understand what I'm talking about, at least. So, hey, now we're reasoning about research ideas. Someday, hopefully this summer, I will find time to code this thing up. And if it works, if it really is faster than a convolutional neural net like I predict, and if it still has the power of convolutional neural nets, that might be an amazing thing for improving the ability of machines to learn to recognize images. And who knows, maybe it works in some way similar to how human sight and mind learn and work. Okay. I want to show you another idea while I'm at it. I gotta remember what this one was called. This is actually a proposal that I put out to the NSF. Not that. Where is it? There. In that proposal was a architecture that I was proposing to build. And I want to kind of talk you through some of the ideas here and see if any of these make sense to you. So, actually, before I do that, I should talk you through a certain learning algorithm. There's a model called A3C. Anybody heard of that? This is a deep Q-learner based model. Deep Q-learning, do you remember I talked very briefly about that paper where they used a learning model to play Atari games? This is a spin-off off of that. A3C is an improvement upon deep Q-learning, and its primary contributions are, well, it has a few of them. Essentially, it's, how can I describe it? Well, it learns continuous controls rather than discrete controls, and yeah, let me just go back to my diagram here. So the A3C model has two outputs. One of them is policy, that is, it chooses what controls it's going to make, so it chooses actions, and the other one is a utility estimate. The idea of utility is it judges how good its controls were. I briefly talked about actor-critic models in a previous lecture. Well, this is, A3C is both an actor and a critic model, but it uses the same neural network to do both jobs. And the advantage of doing that is it enables transfer learning. Okay. As I think about that, I need to explain transfer learning a little bit. Let's talk about transfer learning. Okay. Suppose you have a task. Let's suppose the task is to take a picture of a human and predict, what should we predict about the human? Gender? And let's suppose another task that you have is to take a picture of a human and predict political affiliation. Okay, sorry, I got a sneeze. It's coming. It's dying. Okay, not gonna happen. Whenever I'm about to sneeze, my wife says, pear, 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 pear. And she swears that if you say that, it makes it impossible for somebody to sneeze. I'm convinced that when something is funny to you, for some reason, that diverts the mind away from its capability for sneezing. And yet it's really maddening to me because I have never successfully sneezed while she's saying pear, pear, pear. And obviously pears have nothing to do with sneezing, just like this tangent has nothing to do with transfer learning. Exactly. Okay. Where I was going with this. You train two separate models to do these two separate jobs. How well are they going to work? I don't know. You get so much accuracy. How would that differ from, say, just taking one model and training it to do both jobs and getting rid of them? Give me your assessment. Which one do you think will work better? This or this? So there are a few reasons to suppose one or the other. Now, imagine that this neural network has a limited number of weights, right? Well, if the number of weights is insufficient, then splitting them is probably a better idea, because now every single weight can be dedicated to predicting political party in this one, and every single weight can be dedicated to predicting gender in that one. But here's the question: is there a correlation between gender and political party?
Yes.
There is. It turns out if you survey based on gender, you'll find that a higher number of females are Democrat and more males are Republican, or something like that. I don't know if that's accurate. And it's probably not a lot of correlation, but there is some correlation. But here's probably a more interesting question. While gender alone is correlated, do you think there's anything deeper that could be determined? Well, can you determine gender from a picture? Obviously, usually, sometimes. And can you determine political affiliation from a picture? Maybe. I don't know, not so much. Although, surprisingly, these days you can. Deep learning is eerie in what it can do. And one way you can tell is you can just determine how old they are. Turns out that age is correlated with becoming more conservative. So, therefore, if you just look at the picture and determine how old they are, well, at least you'll get more accuracy on predicting their political party. Therefore, yes, you can. No, you cannot predict it with high accuracy. No, you cannot tell by somebody's face who they voted for in the last election, but you can tell some stuff, all right? And do you remember how we were talking about how there's a paper that recently came out saying, hey, we can actually predict who's gay and who's not based on their photographs? Well, it turns out that is highly correlated with liberal and conservative. Therefore, if you can tell that, you can certainly tell political party. All right. This model would probably do better if you have a crazy large amount of training data. Let's suppose you have very limited training data. Do you see that using those correlations could be an advantage? If we do this type of a model, because there are some correlations between them, even though they're totally different problems, whatever structures it has learned inside, which are represented by this squiggle, that squiggle somehow is the important things of mapping from pictures to gender, which are probably detect whether or not there's hair hanging down behind the ears, mostly, because more girls have long hair than guys, and therefore that alone probably tells you a lot, is just looking at the pixels on either side of the neck. But if the structures inside of there are useful and can be useful for the other problem, do you see that training on the first one actually helps it learn the similar structures for the second one a little bit better, even though it's a different problem? So this is an approach called transfer learning. And this is kind of considered to be a holy grail topic in machine learning, because imagine how good are humans at transfer learning, right? We grow up learning how to rake the leaves and mow the lawn and whatever our dad makes us do, and then we go get a job, and somehow we just know how to do whatever the job needs us to do. The boss needs us to go make coffee and photocopy his reports, and we can do it. How do humans do that? Well, presumably, when your dad was teaching you how to follow directions when you were a child, in your head you learned important things like how to parse his words and how to understand what he meant and how to go do it and how to be on time and all these things. And we transfer the learning that has occurred throughout our childhood into our adulthood life, and it turns out people that don't have parents don't do as well as adults, because transfer learning is a real thing and humans are really good at it. Similarly, when you train a neural network on one problem and then train it on another problem, it often learns the second problem faster than it would if you started from scratch. Isn't that weird and mysterious and awesome and kind of meaningful? Because just the fact that it's learned from one other thing means that it's developed some structures inside, and if there's correlations among them, it tends to work. So what a lot of people are doing is just trying to train one big giant neural network on everything they possibly can, and hopefully it sorts out general intelligence inside. Of course, doesn't work, but we're getting closer. Okay, The A3C algorithm, which is not this is my improvement on A3C,